Imagine a prosthetic hand you control just by thinking about it, you know? Using those subtle electrical whispers from your remaining muscles.
It's incredible potential, isn't it? Really bridging mind and machine.
Absolutely. And researchers have gotten so sophisticated at decoding these signals using machine learning and all that.
Mm,
But then comes the really hard part, getting that complex control into a device that's actually practical.
right. Something lightweight, power efficient, something you can wear all day.
Yeah, day in, day out. It's not just about the clever algorithm in the lab.
Exactly. It's where the lab meets, the messy reality of a wearable device.
Mm-hmm.
We have this amazing algorithm, sure, but the physical constraints.
They're severe. Like comparing a supercomputer to a smartwatch, maybe?
That's a pretty good analogy, actually.
Okay. And that's really the core problem we're digging into today. We're looking at this really insightful review paper.
Hmm.
It pulls together the state of the art on exactly this challenge, how muscle signals EMG, right, electromyography,
Yep. EMG.
how EMG, machine learning, and these tiny embedded computers are all converging or trying to converge.
Trying to build the next generation of prosthetic hands. But the paper also highlights the major roadblocks that are still there.
So our mission today is basically to pull out the key takeaways from this review for you, the listener.
We'll look at the advancements, the specific tech they're using, the clever tricks to shrink these big models down.
And maybe most importantly, the gaps, where we still need breakthroughs to make these things truly effective and, widely used.
Definitely.
So maybe let's rewind just a little bit, look at the history. Prosthetic hands have come a long way.
Oh, absolutely. A fascinating evolution. From purely aesthetic, passive things.
Just for looks.
Right, to active ones, powered devices.
Hmm.
Early on, maybe body-powered or mechanically controlled.
But the big leap, the move towards more natural control, that came with EMG.
That was the game changer. The basic idea is just brilliant. Capture the electrical buzz in the residual muscles.
The same signals the brain is still sending.
Exactly. The signal's trying to move the missing limb.
Mm.
And then you translate those signals into control for the prosthetic.
And decoding those signals, that's been the quest, right? It's evolved over time.
Absolutely. The review lays it out nicely in generations of controllers.
Okay.
So Gen 1, super simple, single-site control. You put one sensor over a muzzle.
Just one spot.
Yep. And the strength of that signal, the amplitude, controls one thing, like how fast the hand opens or closes. Simple, but,
Very limited, like a dimmer switch for just one action.
pretty much, yeah.
Yeah.
Then came Gen 2. And this is actually still pretty common in commercial devices today.
Okay.
Dual-site control,
Yeah.
maybe two sensors. And you use their signals, often with thresholds and a state machine logic,
Uh-huh.
to cycle through different preset grips or gestures.
Okay, I think I know what you mean. Like you flex your bicep hard twice, maybe, to switch from a power grip to a pinch grip. Is that the idea?
Exactly that kind of thing. It gives you more options than Gen 1, for sure. But you have to learn these specific sequences, these training pulses, to switch between modes.
It doesn't sound very intuitive. You're cycling through options, not just doing the thing you want.
It's not. It can feel quite clunky compared to a natural hand,
Right.
which is why Gen 3 was such a big step forward.
Right. What changed there?
Pattern recognition, using multi-channel EMG, so instead of just one or two sensors, maybe 4, 6, 8, even more, spread out.
Okay, more data points.
Exactly. And machine learning, often CNNs, convolutional neural networks, gets trained to see the whole pattern of activity across all those sensors.
Mm.
And it recognizes that complex pattern as a specific gesture. Like, that pattern means open hand, this pattern means make a fist, that one means point.
So you just try to make a fist, the sensors read the overall muscle signature, and the ML says, got it, that's a fist.
Precisely. No more cycling.
Yeah.
Your intention for a specific gesture is recognized directly. It feels much more natural for those discrete grips.
That sounds way better. But there's a but, I'm guessing.
There's a but. It's still mostly classification,
Yeah.
identifying which gesture you want. It doesn't easily give you simultaneous control over multiple joints or that smooth proportional control, like how much you close the hand or varying the force gently.
Right. You can pick fist, but maybe not gentle fist versus strong fist easily, or move fingers individually while closing.
Exactly. Which leads us to the cutting edge, what the review calls the fourth generation, Gen 4.
Okay, the frontier.
This is really the holy grail, you could say, aiming for simultaneous proportional control across multiple degrees of freedom.
So controlling individual fingers, wrist rotation, opening, closing, all at the same time. smoothly.
Just like a biological hand, yeah, that's the goal.
Mm.
And this needs a shift in the machine learning from classification to regression models.
Okay.
And this is where concepts like, well, like muscle synergies become really fundamental.
Okay, let's pause on muscle synergies. That sounds important for this Gen 4 stuff. What exactly is a muscle synergy? Why is it useful here?
So the idea comes from neuroscience, really. It's that your brain, well, it doesn't micromanage every single muscle individually when you move. There are over 100 muscles involved in hand and wrist movement.
That would be incredibly complex.
Totally. Instead, the theory is that the nervous system activates groups of muscles that tend to work together. Coordinated patterns for common movements.
Like pre-programmed building blocks.
Kind of. These fundamental patterns, these underlying units of movement control, are what we call muscle synergies. Think of them like the basic chords your brain plays to create the complex music of a hand movement.
Ah, okay. So instead of mapping dozens of individual muscle signals directly to dozens of motors,
Right.
you try to decode these like underlying synergy activation levels.
Exactly. It massively simplifies the control problem. If you can figure out which synergies are active and how active they are from the overall EMG pattern, you could potentially drive complex multi-joint hand movements using far fewer control signals. It's more like how biology seems to do it, potentially more efficient, more intuitive.
Okay, that makes sense. How do researchers actually, pull these synergies out of that noisy EMG data?
They use various signal processing and machine learning methods.
Yeah.
NMF is a common one, non-negative matrix factorization. It's pretty good at extracting these kinds of underlying additive patterns.
Okay.
PCA, principal component analysis, that's another technique, more linear. And as we mentioned, ML models like autoencoders can sometimes learn these lower dimensional representations implicitly. They can kind of discover the synergies themselves.
Autoencoders, they're neural networks good at compressing data, right?
Exactly, finding the essential features. So the goal is find these synergy ingredients in the EMG and then use their activation levels to proportionally drive the different movements of the prosthetic hand.
Okay, so you've got these really powerful models identifying complex patterns, decoding synergies. Sounds great in the lab. But running that on a tiny chip inside someone's arm, that seems like the big disconnect.
It absolutely is.
Yeah.
That's the central conflict this review really hammers home. The sophisticated ML models you need for that Gen 4 control. They're developed, they're trained, they're run on high-performance PCs.
Which are, too big, too power-hungry.
Too slow sometimes, even if you could shrink them. Just not feasible for a wearable device someone has to rely on all day.
Right. Which brings us to edge computing.
Exactly. The term comes from the Internet of Things, IoT. The idea is you move the computation, the processing, away from the cloud or a big central computer and onto the device itself, onto the edge.
So in this case, the edge is the prosthetic arm, making the AI run inside the arm.
Precisely. On the small embedded processor that fits in there.
How on earth do you do that? Take a big neural network and squeeze it onto a tiny chip. Sounds like magic.
Hey, not quite magic, but definitely some clever engineering. Researchers use specific optimization techniques. Quantization is a really big one. Yeah, you reduce the precision of the numbers the model uses. Instead of, say, full 32-bit floating point numbers, which take up more memory and need more computation, you might represent weights and activations with just 8-bit integers.
Okay.
You can drastically shrink the model size and speed things up, often with surprisingly little loss in accuracy, especially for these kinds of applications.
So it's like using, fewer decimal places, but it still works well enough.
That's one way to think about it, yeah. Another technique is pruning.
Pruning, like trimming a tree.
Sort of. You identify and snip away the least important connections or even whole neurons in the neural network. If a connection's weight is tiny, it's probably not contributing much anyway.
Oh, okay.
So you cut it out. Makes the network smaller, faster. There's also work on things like hyperdimensional computing, which is another way to aim for massive memory reduction.
And there are tools to help researchers actually do this shrinking.
Yes, thankfully. Frameworks are popping up, things like TensorFlow Lite Micro or STMicro's Cube AI. They're specifically designed to take standard ML models and convert them, optimize them, for running on these tiny embedded microcontrollers. It's fueling this whole field called Tiny ML.
Tiny ML. Okay. Now, the review also talks about adding other sensors, not just relying on EMG. Why do that? Is EMG not enough?
Well, EMG is powerful, but it can be noisy. It could be affected by electrode shift, sweat, muscle fatigue, lots of real-world factors.
Right.
Adding other types of sensors can give you a richer, more robust picture of what the user intends and what the limb is actually doing.
Like what other sensors?
Things like accelerometers and gyroscopes, often packaged together in an IMU, an inertial measurement unit. They sense the orientation and movement of the arm itself.
Okay, so where the arm is in space.
Exactly.
Huh.
Or FMG force myography. It measures the pressure changes within the muscle tissue as it contracts.
Right.
You get slightly different information than surface EMG.
So it's like getting multiple witnesses to confirm what's happening.
That's a great way to put it. It's called sensor fusion, combining data from different sources. It can make the ML models much more reliable, less prone to errors from one noisy sensor.
Makes sense.
The review even mentions using explainable AI techniques here to figure out which sensors are actually providing the most useful information, so maybe you can simplify the system later by removing redundant ones.
Interesting. What about cameras? That seems like a whole other level.
Cameras open the door to semi-autonomous control.
Semi-autonomous? How does that work?
The idea is the prosthetic uses computer vision. It sees an object, maybe identifies it as a cup or doorknob or a phone.
Huh?
It can then maybe suggest or even automatically select the best grasp type for that object. Then the user might only need to give a very simple EMG signal, like just a go signal, a simple flex to initiate the grasp.
Ah, so the camera and AI figure out the how, and the user just gives the when.
Exactly. It offloads some of the tricky control decisions from the user onto the device's own intelligence, reduces the cognitive load.
And feedback. I mean, feeling what the hand is doing seems crucial. Otherwise, it's just a tool you're controlling remotely.
Absolutely vital. Sensory feedback is critical for feeling like the prosthetic is really part of you, for integration, and for safety.
Right. You don't want to crush something delicate or burn yourself.
Precisely. Mimicking touch, pressure, maybe even temperature. It lets the user interact more naturally and safely. Technologies like flexible electronic skin, e-skin with arrays of sensors, are really key here.
E-skin. Wow.
Yeah, providing that rich, spatially distributed, tactile information back to the user, maybe through vibration patterns on their residual limb or other forms of stimulation.
Okay, so you've optimized the model, you've got this rich multi-sensor data flowing in, you've got feedback going out. How do you make all that processing happen fast enough on the tiny chip so it doesn't feel laggy?
Yeah, responsiveness is key.
Yeah.
That comes down to careful software architecture and choosing the right hardware. The review mentions different embedded options. Microcontrollers, MCUs, are super low power, but maybe not powerful enough for complex ML. Then you have SOBICs, system on chips, more powerful, can run Linux maybe, handle more complex stuff, but use more battery. And FPGAs, field programmable gate arrays, offer custom hardware acceleration for specific tasks, which can be very fast and efficient if designed right.
Lots of trade-offs there.
Always. And to make it feel real-time, the target is usually under 100 milliseconds response time, so you don't perceive a delay.
Gotcha. Less than a tenth of a second.
Right. You typically need to run different parts of the process in parallel, using what are called real-time threads on the chip. One thread just grabs the sensor data, another runs the main ML model to decide the movement, another sends the low-level commands to the motors. They all run concurrently.
Like a well-coordinated team inside the chip.
Exactly. And ideally, you'd want the system to learn and adapt over time too, right? Muscle signals aren't static. Fatigue, electrode position, even just changes over months.
Yeah, things change.
So having the model fine-tune itself on the device, continuously adapting to the user, that's really important for long-term usability and personalization.
But that's hard to do on the device itself. Training AI usually takes a lot of power.
Another significant challenge, yeah. Most training still happens offline on a PC, enabling effective on-device learning or adaptation for these complex models on resource-constrained hardware. That's an active area of research.
Okay, so pulling back again, looking at the big picture, all this amazing work, the control generations, the AI, synergies, edge computing, where does the review say we actually stand right now?
The review's pretty clear. While we're starting to see those Gen 3 classification models recognizing distinct grips appear in some commercial devices running on-edge hardware.
Okay.
The really advanced stuff, the Gen 4 simultaneous proportional control, especially using muscle synergies, that's still largely in the research lab. Getting that level of complex, nuanced control to run reliably and efficiently on the kind of embedded hardware that can actually go into a practical prosthetic, that's the major frontier right now.
So the algorithms for that better control exist, but making them small and efficient enough is the real bottleneck?
That's a huge part of it, yes. You know, one of the most frustrating things the review points out is something almost basic.
What's that?
a widespread lack of detail in how research is reported. So many papers show impressive control algorithms, maybe tested in simulation or on a desktop PC.
Hmm.
But they don't report the crucial details about the actual hardware they used for testing, if they even tested on embedded hardware. Or they don't report key performance metrics like the real processing latency, the memory footprint, the power draw on those chips.
Why is that lack of detail such a big problem?
Because it makes it incredibly difficult for other researchers to compare different approaches fairly. You can't replicate the findings easily. You can't accurately judge if an algorithm that looks great on paper is actually feasible for a real-world prosthetic arm. It just slows down progress for everyone.
Yeah, I can see how that would be a major roadblock. What other big hurdles did the review highlight?
Well, beyond the reporting issue, there's the continued need to really push the optimization for these complex Gen 4 models, tailoring them specifically for the extreme constraints of prosthetic hardware. Things like really aggressive quantization, maybe even down to binary networks, need more investigation.
Binary networks. Wow, just ones and zeros.
Potentially, yeah. Extremely compact. Then there's generalizability. That's a huge one.
Meaning making it work for different people.
Exactly. Developing models that work reliably across different users, or at least adapt very quickly without needing hours and hours of retraining for every single person. That probably needs much larger, more diverse data sets, and maybe clever use of techniques like transfer learning.
Okay. And latency, we mentioned keeping that delay imperceptible.
Critical. Under 100 milliseconds is the goal. Long processing windows for the AI or complex state machines can easily add too much lag, making it feel unresponsive and unnatural. Getting models to truly adapt continuously, in real time, to the user's changing signals fatigue, limb changes that's still largely unsolved for complex models on device. And finally, the review calls out the lack of standardized protocols.
No common way to test and compare these systems.
Pretty much. We need agreed-upon ways to develop, test, and report performance. Standard metrics that cover both the control quality, like accuracy, how well the output matches intent, maybe using correlation coefficients or RMSE,
Okay.
and the hardware efficiency, the latency, the power use, the model size on the actual target chip. Without standards, it's hard to know if we're really making progress towards practical systems.
Okay, so lots of challenges still. Looking ahead then, what does the review see as the most important directions? Where should the focus be?
They really boil it down to three main thrusts. First, keep exploring time-varying synergies.
Time varying, so synergies that change during a movement.
Yeah, trying to capture the more dynamic, fluid nature of how our muscles actually coordinate, rather than just assuming fixed patterns. It might lead to smoother, more natural control.
Okay, makes sense. Second,
A real prioritization of real-time edge deployment. Stop just developing cool algorithms on PCs. Focus intensely on getting these advanced Gen 4 and synergy-based control strategies running effectively on actual prosthetic-grade embedded hardware.
Yeah.
Using all those optimization tricks we talked about, test it there, report those metrics.
bring the lab work into the real hardware constraints.
Exactly.
Yeah.
And third, significantly enhance the sensory capabilities. Really push the integration of robust, realistic feedback, especially tactile sensing, like with eSkin. They see that rich feedback as absolutely crucial for user acceptance, for safety, and for making the control truly intuitive.
So better dynamics, real-world deployment, and better feeling.
That seems to be the core message for the path forward. It's clearly this intricate puzzle, right? Bringing together neuroscience, sophisticated AI, and miniaturized electronics.
It really is fascinating seeing how all these different fields have to mesh perfectly. We're definitely moving closer to prosthetic hands that aren't just, functional tools, but could feel like a true extension of the user.
And that core challenge, which the review lays out so well, remains bridging that gap. The gap between these incredibly powerful theoretical control algorithms we can design and the harsh practical realities of a device someone needs to wear and trust every single minute of every single day.
It really makes you think, doesn't it? As these devices get smarter, more capable, controlled by our own muscle signals, feeding back sensations that feel like real touch, where does that line between human and machine start to blur? What does it actually mean for a prosthetic hand to stop feeling like a tool and start feeling like just another part of you?